pH curves, which is the first of two videos I'm doing on titrations. Here, using pH curves to find the equivalence point in a titration and the half equivalence point of weak acids and bases. Characteristic shapes and features of pH curves for neutralization reactions, showing that the intercepts with the axis and the equivalence point provide valuable information. Acid-base titrations and neutralization reactions. Neutralization reactions are any reaction between an acid and a base. They do not necessarily produce a neutral solution. However, they do produce water and a temperature rise. Neutralization reactions are exothermic. Titration is a technique used to determine the concentration of an unknown acid or alkali solution. It can also be used to make salts, a product of the reaction. As acid-base titrations do not produce a colored product, an indicator needs to be added to indicate when the equivalence point has been reached. This is the point at which the reaction should be completed. The equivalence point of a titration is the point at which stoichiometric equivalent amounts of both reactants, acid and base, have been added. In an acid-base titration, the equivalence point is the point at which the hydrogen ion concentration equals the hydroxide ion concentration. In the case of a monoprotic acid reacting with a monobasic base, the volume of acid and base should be equal if they have the same concentration. For each titration, the pH can be measured every time a small amount of alkali is added to the acid, and this raw data can be used to draw a pH curve. In most acid-base titrations, the pH curve shows a steepness near the equivalence point as the pH changes abruptly and over a large range of points on the pH scale. If the concentration of either acid or alkali is known, and the reacting volumes of both are measured, then the concentration of the other reagent can be calculated. I will cover the calculation separately in a video on stoichiometry. Titrating a strong acid against a strong alkali, as would be the case with titrating 0.10 molar HCl with 0.1 molar NaOH. The pH of the acid is 1, given by the intercept on the y-axis. When no NaOH has been added, that's the starting pH of the HCl. So we see that we could use my pH curve to give us the original pH of the acid. pH of the NaOH is 13, the final pH when all the acid has been neutralized. I can see that here. Again, the intercept on the y-axis. At the equivalence point, pH is 7, midway between a rapid change in pH, which we can see when the expected 20 ml of NaOH has been added. A rapid change in pH and the equivalence point being halfway through that rapid change. The endpoint of a titration is the point where the indicator changes color, and it's measured experimentally. The equivalence point is when stoichiometric equivalent amounts of acid and alkali have been added. Can be calculated theoretically. Now we're looking at titrating a weak acid with a strong alkali. My weak acid being ethanoic acid, my strong alkali sodium hydroxide. And in the example, concentrations of the two are the same. If I begin with 20 ml of my weak acid, Looking at the equation, I would expect to get the same volume of strong alkali added. And I can see here the rapid change in pH goes when we've added 20 ml of NaOH. My equivalence point being the point between the lower and the upper regions of that rapid change in pH. At the equivalence point, the pH is above 7, which we'd expect. Ethanoic acid beginning with a pH of very roughly 4, NaOH, again, very roughly 14. I'd expect my equivalence point to be around pH 9. Now, a narrower range of pH values is covered. Yeah, I've got a narrower change in pH at the equivalence point compared with strong acid with strong alkali. My indicator must change color at a pH above 7 at the equivalence point. Now that means the pK of the indicator must be above 7. Phenolphthalein, pKa 9.5 or thereabouts, works. Very important point. Halfway to the equivalence point. That would be when, let's say, 10 ml of NaOH have been added. The pH at the half equivalence point. Now, half of the acid has been neutralized, forming the conjugate base A-. If half has been neutralized, half remains. Concentration of the acid at this point equals the concentration of A-. Given my equation for the dissociation of the acid, realizing that the concentration of A- and concentration of HA are the same, we can see that Ka equals the concentration of H+, or pKa equals pH. At the half equivalence point, the pH gives the pKa of the acid. The buffer region is when we have some unreacted acid and the salt both present, round about here. Strong acid, weak alkali. Similar situation. My strong acid here, HCl. My weak alkali, NH4OH. Here's my equation. Now, my equivalence point is below 7. HCl having a pH of perhaps around 1. NH4OH having a pH of around 9. Equivalence point halfway, around about 5. Now, methyl orange has a pKa around 3.5, so is a good choice of indicator. Half equivalence point gives the pKa of the weak base. Half equivalence point when I've got half of my weak base consumed and half of my salt added. I've never seen this asked, but that would be around here on the graph. Buffer region again is when we have some weak base in existence with its salt. Finally, titrating a weak acid with a weak alkali. For example, ethanoic acid with ammonium hydroxide. There is no rapid change at the equivalence point, no clear endpoint. And so these titrations are inaccurate and are never carried out. There is no clear endpoint as a complex system of buffers is produced. We still have an equivalence point when equal number of moles of acid and alkali have been added, but there's no clear endpoint. Again, equivalence points can be calculated from the equation. Endpoints are measured experimentally. Last thing to say, equivalence points I have seen called as stoichiometric points. That's it. If you got anything from that, please hit the like button. Please subscribe to be informed of more content.